All right, in lesson 7, rational functions and their properties. We're going to read and use arrow notation. We're going to find domain and range of rational functions. We're going to find vertical, horizontal, and slant asymptotes. We're going to determine coordinates of holes in a graph, and we're going to use the properties of rational functions to analyze and graph. All right, so the first part here, it says that polynomial functions are seen as functions with integer powers that are non-negative. In the next few lessons, we turn our attention to explore functions with variables in the denominator. The definition of a rational number is a ratio of integers. Similarly, ratios of polynomial functions are known as rational functions. Just remember, guys, rational means fractional. Okay, so if you hear the word rational, you know it's going to involve a fraction. All right, so the domain of the domain for polynomial functions is all real numbers, but the domain of a rational function will be restricted from any values of x that cause division by 0. So it says, let n of x, our numerator, and d of x, our denominator, be polynomial functions where d of x cannot equal 0. Then a rational function is, so our rational function, which we're going to call r of x, is equal to n of x divided by d of x. All right, so example 1 says find the domain of this function. And so remember with domain, we've talked about this because it's been showing up off and on since we started school. We have those certain restrictions for domain, and one of them is if it is a fraction, we remember that our denominator cannot equal 0. So in this case, x squared minus 8x plus 12 cannot equal 0. And so we factor this out. So we can use our x box. So let's see, it's got to multiply to 12 combined to negative 8. So let's see, what is that? Negative 6 and negative 2. So we got x minus 6. X minus 2 cannot equal 0. So set them each not equal to 0 and solve. And so we get x cannot equal 6 and x cannot equal 2. And then we can do our number line to help us out here. So I'm going to put my infinities, put my 2 and my 6. If I can't equal them, remember, that means you can equal everything else. So everything to the left, everything in between, and everything to the right. And so we can see that our domain is infinity to 2, union 2 to 6, union, and 6 to infinity. All right, so then they talk about reading arrow notation. So throughout this course, we will use arrow notation to show that x or f of x is approaching a particular value. And we saw this with limits when we were talking about the end behavior earlier. So the table below is a summary of proper notation and how it is read. So let's go over it quickly. So we see here the first one says as x has an arrow with an A, and it looks like it's raised to a negative sign. So we read that as x approaches A from the left. So if you think about your number line, here's 0, your negative numbers are over here on the left, and your positive numbers are over here on the right. So as x approaches A from the left. So then we have as x approaches A from the right, because it's got a little positive. Then as x approaches positive infinity, x approaches negative infinity. So then we have f of x is approaching A, or we could say the y value is approaching A, the output is approaching A. Then we have f of x is approaching positive infinity. Again, we could say the output, we could say the y value, and then f of x is approaching negative infinity. All right, so let's talk about horizontal and vertical asymptotes. So a vertical asymptote is going to be written, it's vertical, so it's a vertical line, so it's an x equals equation, and it's x equals some number, and we're just going to use the letter A to represent a number here. Okay, it says the graph behavior will approach the vertical line and either increase or decrease without bound. All right, well, first let's talk about a vertical asymptote. So a vertical asymptote is going to be a vertical line that your graph is going to get super, super close to, but it will never, ever cross it, okay? So like we can see in this one here, the red line I just drew in is our vertical asymptote. Both sides of the graph are going to get really close to it, but they're not actually going to touch it. And so we can talk about what's happening to our graph at those places using, or at that spot, using limit notation. And so that's what it's talking about here, that it's either going to increase or decrease without bound. So we can see that from this left side, our graph is going up, and it's going to keep going up without bound. Okay, and so that's what it's talking about right here on this first limit. It says the limit as x approaches A from the left. Well, for ours, where is our vertical asymptote? It looks like it's at -3. And so we could say the limit as x approaches -3 from the left, what's happening to f of x? What's happening to our function? We just said it's going to increase without bounds, so it's going to go up to infinity. And then we can see on the other side of the graph, so as I'm coming from this direction, look at how I'm drawing it, the side I'm coming from the right side going towards that -3, and my graph's going to decrease without bound. It's going to keep decreasing. So we could say the limit as x approaches -3 from the right, f of x equals, in this case, it's -infinity. But either way, when you're looking at the limits here, because it's going to increase or decrease without bound, it's either going to go to positive or -infinity for both of these, okay? They typically don't go the same direction. They usually go opposite directions. If they go the same direction, I would investigate it a little bit more to make sure they're not connecting way up high. But there is a chance that it could go in the same direction. All right, then we have horizontal asymptotes. Horizontal asymptotes are a horizontal line that my graph is going to get super, super close to, but it will not cross it at the ends of the graph. So it's looking at that end behavior on the far left and the far right of my graph. This one here doesn't have it crossing in the middle, but it could cross it in the middle of our graph. All right, a horizontal asymptote is a horizontal line, so it's going to be y equals some number, and we're just going to let b represent that number. All right, the graph behavior will approach the horizontal line as x is going to the left or to the right. So as x is going to -infinity or positive infinity. And so that is, it says the limit as x approaches -infinity, f of x equals, and you'll put a number there wherever that horizontal asymptote is. Or the limit as x approaches positive infinity, f of x will equal, and you'll put a number as well. All right, so for this one, we can see our horizontal asymptote is right there at 2. So as our x is going towards -infinity, we can see that our y values are going to get super duper close to that line, but they're not going to cross it. So they're going to get super close to 2, but not cross. And the same thing as we're going towards positive infinity. So if I look at my graph here, and you can see I'm drawing it, that as I go towards positive infinity, my graph is going to keep getting closer and closer and closer to that asymptote, so my y's are going to go towards 2. And then it did talk about here, what I had mentioned, it said it is possible to cross a horizontal asymptote. It's the only asymptote we'll actually cross. The graph does not have to have the same behavior on both sides. Usually it will, but it does not have to. All right, and then we have 3 cases. 3 things that can happen. So the first thing is that the degree of the numerator could be less than the degree of the denominator. So for example, we might have the equation y equals x minus 2 over x squared minus 9. We can see here that our degree on the top is 1 and the degree on the bottom is 2. 2 is bigger, so the top is smaller. So if that's the case, then the line y equals 0 will be our horizontal asymptote. Then we can have the second issue, or second case we could have, is the degree of the numerator can equal the degree of the denominator. So for example, we might have the equation y equals 8x squared minus 1 over 2x squared plus x minus 3. If you have this happen, then the ratio of the leading coefficients is the horizontal asymptote. So the ratio of the leading coefficients, remember the leading coefficient is the number in front of the x with the largest exponent. So in this case, it would be these two. It would be the ratio of 8 over 2, which then this one would have a horizontal asymptote at y equals 4. So over here it says that is y equals, and they just put it as a over b. That was just a ratio of two numbers. And then the third case is if the degree of the numerator is greater than the degree of the denominator. So for example, if we have the equation y equals x squared minus 5x plus 4 over x minus 2. In this case, we can see the degree of the numerator is bigger, and that means that there's going to be no horizontal asymptote. And so I use a little shortcut to help us remember horizontal asymptotes. So for horizontal asymptote, I just remember it's going to be no, or I have to know it's going to be the ratio of those leading coefficients. Okay, I put the n on top because if your largest exponent is on top, it's none. There is no horizontal asymptote. If your largest exponent is on bottom, it's y equals 0. So it's no. All right, and so example 2 says to find the horizontal asymptotes for the given functions and provide a reason. So look at A. Where is your highest degree? It's on bottom. Remember that 1 has an x, it's just x to the 0, okay? So because x to the 0 is less than the x squared, it's on bottom, so I'm thinking I know that my horizontal asymptote is going to be y equals 0. It's on bottom, that O is for y equals 0. All right, so for B, my degree is the same. So remember, if they're the same, it's just going to be the ratio of those leading coefficients. So it's going to be that 3 over the 1 right there. And so we get y equals 3. And so our reasoning will be that our x to the first on top is equal to the x to the first on bottom. And then our last one there, we can see that the x squared is larger than the x on bottom, so because x squared is greater than x, but I use the no, since the largest is on top, I know that n stands for none, so my horizontal asymptote is none. Yep, shouldn't box that. I didn't put a horizontal asymptote on this one either. All right. Then we have a slant asymptote. And so a slant, or they call it an oblique asymptote, occurs when the degree of the numerator is 1 higher than the degree of the denominator. The slant asymptote is a quotient polynomial found from using synthetic or long division. So example 3. Well, first, it's going to be a slant, or they call it an oblique asymptote. It's literally a slanted line. Okay, you can only have a slant asymptote if the degree on top is bigger than the bottom by 1. So like x squared over x, or x cubed over x squared, x to the 10th over x to the 9th, okay? The top has to be bigger by 1. And so example 3 here says determine the slant asymptote of this function. So we have two options. We're going to find our slant asymptotes by using synthetic or long division, okay? So before I can choose which one I want to use, I need to look at what I'm dividing by. Remember, we're only going to use synthetic division if it tells us to, or if it's being divided by x and then plus or minus and some number. And so on this one, I can use synthetic division. So when I go to do that, because I'm dividing by x plus 5, I use its 0. So x plus 5 equals 0, which means x will equal negative 5. So when I go to do my synthetic division, I'm going to put a negative 5 there. I've got to make sure that the numerator is in descending order of the exponents, and every exponent from the largest one down is accounted for. So like I have an x squared here, I have to have an x squared, an x, and a constant. If any of those are missing, I just put a 0 in its place. All right, so its coefficients are 1, negative 6, and 7. Below the constant, put a little box. Remember, that's your remainder box. Now, we did not say that the x plus 5 here is a factor of the numerator, okay? We may have a remainder. We may have a remainder. So let's find out. So we're going to bring down the 1. Remember, anything on the bottom row gets multiplied by that negative 5 on the outside and put into the next column. Combine them. Multiply that by negative 5. And I got 62 as a remainder. All right, so my answer here then is y equals, we started out with x squared, so our answer is going to start with x, so 1x minus 11, and technically we would say plus our remainder over what we divided by, which is the x plus 5. But now let's think about this. As my x gets bigger and bigger and bigger, what's going to happen to that fraction? All right, so I'm just going to use smaller fractions. So we have 1/2, 1/4, 1/8, 1/30. Those numbers are getting smaller and smaller and smaller as that denominator gets bigger and bigger and bigger. So as x gets bigger here, this denominator is going to keep getting bigger and bigger and bigger, till eventually my fraction is going to be worth nothing, okay? So when we're doing the synthetic division for our slant asymptote, because it's dealing with the end behavior, our x's are going to get really big, we don't worry about the remainder. So our slant asymptote is just going to be y equals the x minus 11. All right, finding holes, vertical asymptotes, and x-intercepts. All right, tells us here, if r of x is equal to n of x over d of x is a rational function, and if n of x and d of x have no common factors, then the rational function r is said to be in lowest terms. We find x-intercept. All right, so let me start there first. All right, so we're going to factor it out and make sure that nothing can cancel. We want it to be in lowest terms. Then we find the x-intercepts by setting the numerator equal to 0, while both holes and vertical asymptotes are going to be found when setting the denominator equal to 0. So here are some steps to keep in mind when analyzing rational functions. So number 1 is you want to simplify the rational function by factoring both the numerator and the denominator. You want to find the zeros of both the numerator and the denominator. If the 0 is common to the numerator and the denominator, you have a hole. And so this would be like if we had a canceled factor. If we just look at it in factored form. If 0 is unique to the denominator, you have a vertical asymptote. And if a 0 is unique to the numerator, you have an x-intercept, a root, or a 0, whichever way they want to word it. All right, so let's try this. It says find the holes, vertical asymptote, and x-intercepts for the following rational function. All right, so I'm going to simplify. I'm going to factor this out. Now, according to what they told us on the previous page, they said that we're going to find the zeros of the numerator and the denominator. So for the numerator, that's where our x times x minus 3 will equal 0, which means x equals 0, x minus 3 equals 0, so x equals 3. For our denominator, it's going to be where 3x times x plus 2 equals 0. So 3x equals 0, x plus 2 equals 0. Divide by 3, subtract the 2. All right. Now, it tells us that we have wholes. If a 0 is common in the denominator and the numerator, you have a whole. So, do I have anything in common here in both of these? I do. They both have x equals 0. So that means I do have a whole at 0, comma, some number. Okay, now to find that number, so we know our x is 0, we need to plug our x into our equation and solve for the y. But you've got to do it in its simplified form. So I'm going to keep going on this. These x's would cancel. I'm left with x minus 3 over 3 times x plus 2. So that's the equation I'm going to plug into to find my y value. So I'm going to plug in that 0 minus 3 over 3 times 0 plus 2. And I got negative 1/2. So that means I have a whole at 0, comma, negative 1/2. And then it tells me that if the 0 is unique in the denominator, we have a vertical asymptote. Well, let me change colors here. All right, so vertical asymptote. If we have anything unique in the denominator, that's going to be that x equals negative 2. All right, and it tells us that if a 0 is unique in the numerator, we have an x-intercept, 0, root, whatever they want to call it there. All right, so my x-intercept. Do I have any that are unique to the numerator? That's that x equals 3. So x equals 3 is going to be my x-intercept. Or we could write it as an ordered pair. We could write it as 3, comma, 0. All right, and that's the end of the first part of Lesson 7.